Good day, grade 12s. My name is Isabel van Gent, and today we are going to look at the chemical industry. The chemical industry, as referred to in this chapter, rather deals with the chemistry behind fertilizers than anything else. So why do we need all these fertilizers? I suppose it's common knowledge that there are 7.8 billion people in the world, and it is growing daily. All those people have to eat and stay healthy, and therefore there is huge pressure on food production. So there's the growing population, we need more food, and plants are the primary providers of food for all mammals. Of course, that is animals and people. So we need more wheat, corn, vegetables, legumes, so that it can sustain the animals as well as the people, so that people can have vegetables as well as some meat. In order for plants to produce optimally, we need sufficient nutrients so that they can supply us with enough plant-based foods. Let's look at the nutrients for plants, and more specifically to the definition for that. So a nutrient to a plant is a chemical substance used for the metabolism and the physiology of an organism, and it is absorbed from the environment. So that is a very long definition, but that is what you have to write down when that is asked in the exam. We can distinguish between two types of nutrients: macronutrients, which means they are present in large quantities and are needed in large quantities. And also you will see that I wrote there, that is CHO and NPK. There's method behind that madness because it's much easier to remember CHO and NPK than carbon, hydrogen, oxygen, and then nitrogen, potassium, and phosphorus. This is a summary series, so it is important to note that we will often make use of much shorter notations. As you all know at this stage, C stands for carbon and H stands for hydrogen, and it is much easier to remember CHO and NPK than the long words. That's just a word on that. As we progress throughout this presentation, that will be used quite often in the shorter format. So the macronutrients are what is needed in large quantities, CHO, NPK. And the opposite to that are the micronutrients, which are absorbed in small quantities, iron, copper, and zinc, and then chlorine is the one a bit outside of that, but plants also need micronutrients to flourish. If we look at the nutrients, we can further distinguish between different types. We've already spoken about the macro and the micronutrients, and within the macronutrients, CHO, NPK, we can distinguish between non-mineral and mineral macronutrients. The non-mineral nutrients are CHO. You have already met these three characters quite intensely in organic chemistry. So you can also associate the non-mineral nutrients with what you have learned in organic chemistry. And then on the other side, we have the mineral nutrients, and that is NPK. So now we split the family of CHO and NPK up into minerals and non-mineral nutrients. If we look at the non-minerals, we need to find out what is the source of that. As you can see, carbon dioxide plants absorb from the air, and then H and O is present in our very well-known friend water, H2O, coming from the rain. In other words, it's coming from the air, but in the form of rain, and then that water that the rain is supplying, or perhaps irrigation, is absorbed in the soil. So the non-mineral nutrients are basically coming from above, the ground level, and the mineral nutrients are present as nitrates, phosphates, and potassium ions. They are soluble in the water in the soil, and therefore the plant can absorb them through their roots. I just want to talk briefly about the little image that I used there. I'm going to use it quite often. I want to draw your attention to the fact that our brains remember pictures much more than, and much more easily than it remembers words. So I want to urge you to use these pictures to actually remember these, where these nutrients are coming from. And that is going to be used quite often so that you can get used to that. So we've already touched on the source of the nutrients. As you can see in this table, we also have to know what the function of the nutrients are in plants. On the left, and in the top 3 lines, we have the non-mineral nutrients, our friend CHO. We've already established that they are all coming from the air, and they are absorbed as water through the precipitation falling down as rain, and all of them have exactly the same function. They are part of carbohydrates, lipids, and proteins in the plant. As we all know, the first letter of nitrogen is N, and we can associate that with proteins. So nitrogen is part of the plant proteins and of chlorophyll in the plant. If we go to P, phosphorus, the first 2 letters is pH. That has a role in photosynthesis, plants to flower well, and for root growth. The last mineral nutrient, potassium, that is important in cell building, and it is part of chlorophyll, and potassium is the doctor of the plant because it reduces diseases. Just another idea perhaps of how you can remember the functions. Potassium to me sounds like potato, and potatoes make you strong, so we can associate that with the cell building, and then part of chlorophyll, and as I said, it reduces diseases. Once again, I am showing you the image of the plant to show you that CHNO, the source of that is above the ground, and that N, P, and K are sourced below the ground in the soil. Once again, I'm showing you the image of the little seedling so that you can just consolidate that the non-mineral nutrients are coming from above the ground and the mineral nutrients are absorbed from the soil. That brings us to fertilizer. Let's look at the definition for fertilizer. A fertilizer is a chemical compound that is given to a plant to promote growth. Fertilizers are the providers of N, P, and K to plants. As we said before, it is absorbed through the roots, but it is actually applied on top of the soil. It dissolves in the water in the ground, and the roots can absorb it. Types of fertilizers are used. On the one hand, we get organic fertilizer. I don't have to remind you where that is coming from. That picture shows it clearly. It is made from natural products like manure and compost. Quite logically, the opposite is inorganic fertilizer, which is industrially produced, and you buy it in containers like the bag we show you there. At this stage, I would like to show you exactly what this inorganic fertilizer looks like. Sometimes we talk about stuff and then it sounds like Greek to some people, and then it's always good to show people what stuff looks like. So over here in my hand, I'm going to throw some inorganic fertilizer which has been industrially produced. It looks like big grains of sand. All fertilizers are fairly soluble, actually very soluble in water. And I just quickly want to show you, if we throw it a bit in the water, swirl it a bit. It will take a while, but it will dissolve. We previously said that nitrogen, phosphate, and potassium are present as water-soluble nitrates, phosphates, and potassium ions. So what will happen in a while is that it will dissolve, and the chemical substances in there will actually dissociate, and the nitrates, phosphates, and potassium ions will be available for absorption. Just by the way, this is an endothermic reaction. So if you want to do it at home, get a bucket with a bit of water and steal some of mum or dad's fertilizer, and you can actually feel the temperature going down as it is dissolving. Let's just leave this for a while, and we will then see that all those granules will dissolve. So while the fertilizer is dissolving in the water, we will also then at the same time have a look at how do we know how much fertilizer is in here. Because certainly if a farmer or any other agricultural expert must fertilize his lands, they must have some other idea of how much fertilizer they add to the soil. So over here we see a bag of fertilizer, and the top part says NPK ratio. So let's have a look at what is indicated on this bag. In the middle there in the blue strip, we see the numbers 2, 3, and 2. So the first number on the left refers to the quantity of nitrogen present. The next one, the 3, to the quantity of phosphorus present, and then the other 2 to the quantity of potassium present. So 2:3:2 is a mass ratio of nitrogen to phosphorus to potassium. It is important at this stage to note that not all fertilizers have that ratio. It depends on the final application and on what the agriculturist or the farmer wants from his plants. It depends then on what type of ratio he applies. That could also be 3:1:5, for instance, where the potassium content is much higher, the phosphorus content is then 1. So 3:1:5 would then mean there's 3 parts nitrogen, 1 part phosphorus, and 1 part potassium. Then there is another important number indicated on the bag. In brackets, after 2:3:2, we get, in this case, a number 14. That means that of that whole bag, only 14% of the contents consist of N, P, and K. The rest, 86%, that consists of sand and fillers. It will also be required from you to calculate the mass of nitrogen, phosphorus, and potassium in a particular fertilizer, and you can be given any NPK ratio to do that. So in our problem here, we have the situation where it tells us, calculate the mass of nitrogen, phosphorus, and potassium that is present in 500 grams of industrial fertilizer, with a NPK ratio of 5:2:3, and in brackets, the mysterious number of 40. So 5:2:3 implies that there are 5 plus 2 plus 3 equals 10 parts of N, P, and K in total of the percentage containing N, P, and K. The next mysterious number, that 40, as we saw on the bag in the previous slide, that indicates that 40% of the total mass consists of N, P, and K, and if we do the calculation, 40% of 500 grams is equal to 200 grams. So in this case, we have to calculate the mass of N, P, and K in this 500 gram sample. So obviously, 5/10 of the mass of the 200 grams will consist of nitrogen, and that gives us the answer of 100 grams of nitrogen. Do similar calculations for phosphorus, which consists of 2 parts of the 10 parts, and that gives us an answer of 40 grams of phosphorus, and for potassium, 3 parts out of 10 yields 60 grams of potassium. So, our problem statement said we have a bag of 500 grams of fertilizer. We already know that 40% of this, which is equal to 200 grams, are N, P, and K. Whilst the bottom part consists of fillers and sand, and we ignore that part. we do not have to calculate anything with regards to that. So in the 500 grams of fertilizer, we only look and we're only interested in the 200 grams that contain nitrogen, phosphate, and potassium. Right. Then, on top of having to calculate the mass, we also sometimes have to calculate the number of moles of N, P, and K. We know that there are 100 grams of nitrogen, 40 grams of phosphorus, and 60 grams of potassium. If we have the mass of a substance, and if we can find the molar mass of a substance, we can calculate the number of moles. So, the molar mass for nitrogen is 14 grams per mole, and we use the well-known formula N equals the mass over the molar mass, and in this case the mass of nitrogen is 100, the molar mass is 14, so we get 7,14 moles. Please note that phosphorus and nitrogen and potassium are elements on the periodic table, so we can look up the molar masses for phosphorus and potassium and do similar calculations to find out how many moles of those elements are in our bag of fertilizer. Right. We have already looked at the table which says what is the purpose and the function of each type of fertilizer in the plant. We don't have to use one type of fertilizer for every application that we want. We can use a fertilizer with a certain combination of N, P, and K for specific reasons. If we again look at the function of nitrogen, so nitrogen promotes leafy plant growth, and it is very effective for faster growth on lawns and other plants. If we look at phosphorus, let's look at the picture first. What do we see there in that picture that's prominent for me? It stands out that we don't always see the tree and its roots. And it is a tree that is bearing fruit. So if we remember the picture, we can associate the application of phosphorus for strong roots, healthy fruit, and flowering, because before the fruit came, there must have been a flower, on trees and flower beds. Our last element in this table is potassium, and remember we said it's the doctor of the plant, so let's look at this picture. A rather sick-looking tree with brown leaves and fruit on that. Potassium promotes disease resistance and the growth of fruit. We already saw that nitrogen is a very important mineral to promote growth in plants. So let's look at the production of nitrogen compounds as components of fertilizer. And just to give you an idea how this is all playing out and where it is coming from, I would like to show you a little video of how nitrogen compounds are produced.
Let's have a closer look at one of these plants. It's located in Sluiskil in the Netherlands. Yara Sluiskil is a modern plant producing different types of nitrogen fertilizers. The plant, with its own port, covers 135 hectares and employs 600 people directly and approximately 3,500 people indirectly. It is composed of several areas dedicated to different production units: ammonia, nitric acid, urea, UAN, and ammonium nitrate. Sluiskil also benefits from a port allowing access to the sea. The four main production units are shown here again schematically. In a modern plant like Sluiskil, ammonia, an important intermediate product in fertilizer production, is produced from air and natural gas. The natural gas comes in from the North Sea through a dedicated pipeline. In several production steps, nitrogen from the air is combined with hydrogen from natural gas to form ammonia. Let's now have a look at the different stages involved in the production of fertilizers.
As we could see from the video, all the nitrogen compounds are actually made on one premise. in one factory. There are different departments in the factory, and they all manufacture a different nitrogen compound. Nitrogen is applied to the soil as ammonium nitrate. That is one option. And if we look at ammonium nitrate, it is quite clear from the chemical formula that it must consist of ammonia and one or other form of nitrate, and that is chemically bonded to form ammonium nitrate. This is important to analyze the molecules like this, because it actually takes a lot of rote learning and hard remembering out of the equation for you. Nitrogen is also applied as ammonium sulfate, and as you can see, the building blocks are ammonia and sulfuric acid, H2SO4. And then the last one is urea. There's a CO squashed between two NH2s. So for me, there must be some ammonia that is forming the building blocks and maybe some CO2. We will have a look at this at a later stage, exactly how these chemical reactions are putting the urea together. It is very important that for examination purposes you must know all the chemical reactions and the names of the processes to form these compounds, and we will have a look at that just a little bit later in the presentation. Besides the N compounds, there are also the phosphorus compounds as components of fertilizer. The phosphorus is applied to the soil as calcium phosphate, and that is called a single superphosphate. And the building blocks of phosphate rock that is reacted with sulfuric acid. And then if phosphate rock is treated with phosphoric acid, it produces triple superphosphate, which is a very potent fertilizer. Potassium is a relatively easy one, as it occurs as very soluble potassium salts, such as potassium carbonate, potassium chloride, potassium sulfate, and potassium nitrate. It is mined and it is extracted from mineral rock. So lastly, we have compound fertilizers, which contain both nitrogen and phosphorus, and it is produced by reacting calcium phosphate with nitric acid, and then you get this very super fertilizer that contains both nitrogen and phosphorus in one molecule. Grade 12s, let's have a look at the production of ammonium nitrate. As you can remember, I said a while ago that we will have a look at all the chemical reactions that is forming this molecule. So on your screen is appearing NH4NO3. On the left, for me, it looks like NH4 is definitely family of ammonia, and the NO3 is a nitrate ion. Let's have a look where that originates from. NO3 is actually coming from nitric acid, and it reacts with ammonia to form ammonium nitrate. Grade 12, the method in the madness of starting with the end product of this process is an attempt to show you that you do not have to rote learn all these chemical equations. If you can write out a chemical equation and balance a chemical equation, you only have to know what the sequence of reactants are in order to produce a certain product. And that is what we are going to have a look at now. We have ammonia in the middle of the screen, so let's see where ammonia is coming from. Remember when we looked at the video, it clearly showed that there's a section in the factory that's producing ammonia. The production of ammonia is called the Haber process. Grade 12, it is very important that you must know the names of the processes to form each substance. So let's look where ammonia is taking us now. Somehow or the other, we must make nitric acid from ammonia. So if we look at ammonia, Then we react it with oxygen to form nitrogen oxide. Very important, there's a catalyst. PT is the chemical name for platinum. That process is called the catalytic oxidation of ammonia. If you look at the reaction, you don't have to remember that very difficult looking name. What are we doing? We're adding oxygen, so that is oxidation. What are we adding oxygen to? Of ammonia. And there's a catalyst. So the process is then the catalytic oxidation of ammonia. If we look at nitrogen oxide on the left and compare that with nitric acid, we can see that we still need to add a few more elements to get to nitric acid. The next one, an intermediate product, is nitrogen dioxide. So what do you think they've added to nitrogen oxide to get to nitrogen dioxide? My best guess was another oxygen molecule. Right, so now we are at nitrogen dioxide. We have 2 oxygens and 1 nitrogen, and we still need to get to nitric acid. So what do we need? There's an H there and another O. So maybe our old friend water will do the trick. I just want to go back to something that I said earlier. If you know what the sequence of the formation of the substances is, then you can easily work out what you have to add, and you can just write the balanced chemical equation for that. Okay, so that whole process of forming nitric acid is called the Ostwald process. I associate the O of Ostwald with the oxygen. We must just bear in mind that later on we have another oxygen addition and then it's called something else. But in this case, I associate the oxygen addition with Ostwald. Okay, next one. Urea. The 2 ammoniums, looks like 2 ammoniums to me, with something of a carbon dioxide squashed in the middle. Let's look at what has reacted to form urea. It seems to me that my prediction is correct. Ammonia and carbon dioxide. As we have seen in the video, the factory has a dedicated section where ammonia is produced, and they're not going to follow another process. They are going to use the Haber process again to produce ammonia. And our other old friend, carbon dioxide, is abundant in the air around us, so they just need to isolate that and react it with the ammonia, and we get a very good fertilizer, urea, with actually 2 nitrogen atoms in the molecule. Let us have a look at the production of ammonium sulfate. This is the last molecule that contains nitrogen. So that is what ammonium sulfate looks like, NH4, 2 times, and SO4. So now we already know that in all these processes, our old friend is ammonia. And the SO4 part to me looks like perhaps they've added sulfuric acid and ammonia together. Right. And of course, ammonia is produced during the Haber process. Now we must just look at the substances that form sulfuric acid. So we've got H2, S, and O4. So first of all, we combine sulfur and oxygen to form sulfur dioxide. And then the next reactant in the process is sulfur trioxide. So what do we need to add from dioxide to trioxide? Another oxygen. But once again, this needs a catalyst called vanadium oxide. So this process would be called, I haven't indicated it on the screen, so let's deduce it from the previous reaction where we used a catalyst. So this is the catalytic oxidation of sulfur dioxide to form sulfur trioxide. So if we look at sulfuric acid again, so from the sulfur trioxide, we need another oxygen and 2 hydrogens. The process to form sulfuric acid from sulfur, oxygen and water is called the contact process. So grade 12s, once again, I hope that these diagrams will help you to remember the sequence of the reactants in some places and substances in the others, to write your own balanced chemical equations and to make this a lot easier for you. So all of these ammonium compounds are actually coming together when they are put together in inorganic fertilizers. All those compounds are actually going into these granules so that it can be applied to the soil. So, inorganic fertilizers have some definite advantages. As we have seen in the slide that contains the big bag of fertilizer, we know exactly what's in there, so we can accurately control what we apply to the soil. It is water soluble, as you have seen here, and we can actually use less inorganic fertilizer for the same result as when we use organic fertilizer. But then unfortunately there are some disadvantages as well. It's an industrial process. I want to take your minds back to the video. Did you see some smoke? Yes, definitely. So it's an industrial process, so there's huge cost with regards to that, as well as a polluting factor. And then very important, if the farmer has used too much fertilizer and not all of it has been absorbed by the plants, as we said before, all of that is soluble in the water in the ground, so that can run off into rivers and dams and poison the soil. The poisoning of the rivers and dams has got a name, and that is called eutrophication. If we look at the definition of eutrophication, it is the process by which an ecosystem becomes enriched with inorganic plant nutrients, especially phosphorus and nitrogen, resulting in excessive plant and also algae growth. And that is because as the plant growth becomes excessive, the amount of dead and decaying material from those plants increase rapidly. It is important to note that as the decaying matter increase in water, the oxygen levels of the water becomes depleted. And fish may die in huge numbers, which further contribute to the toxicity of the water and for it not being fit for human consumption or for the consumption by animals. So eutrophication causes pollution due to excess plant growth. It makes the treatment of drinking water very difficult. It decreases the biodiversity, and we get huge occurrences of toxicity due to flourishing algae and all the plant and animal matter decaying in the water. So let's look at organic fertilizers as the opposite to the inorganic industrially produced fertilizers. Once again, the source, compost and manure. So in organic fertilizers, the level of the nutrients are lower, and the time that it takes plants to absorb it is much longer. That is due to the decay that must first take place and the nutrients that must become available in soluble form for the plants to be absorbed. But due to some undigested plant material in manure, it improves the physical structure of the soil. Also remember that there's a lot of cellulose that I referred to in the previous point that has not been digested, and that can absorb water in the soil, and it improves the water holding capacity of the soil. So the release of nitrogen, phosphorus and potassium is much slower, and that implies that water pollution is decreased when organic fertilizers are used. I'm showing you a blank screen at the moment, grade 12, because I'm going to show you a series of pictures, and I want to challenge you to try and remember what these pictures are. We are also going to have a good chat about that afterwards, but I'm trying to instill in you to rather use pictures to learn from than just words. Unfortunately, 2 examples of poop. And I'm using that horrible word on purpose because we also do remember stuff that's funny or bizarre or horrible, much better than we remember normal words. So on the left we have our manure, and then the next one is an island full of guano. That's actually the excretion of seabirds. Over there it looks like a bed of white stones. It's actually lime. And over there we have different lands planted with different crops. And the last one is a pinkish brownish crystal, and that is called potash. The reason why I am showing you these images, because they are the alternative sources of inorganic fertilizer. We looked at the 5 images in the previous slide, and now we are going to take a closer look at the characteristics of each of these sources of inorganic fertilizer. So our famous cow poop, called manure. The reason why I call it the poop is so that you don't forget about it. High in NP and K, slow release of those nutrients, it adds organic matter to the soil, and the nitrates are very soluble in water. We have already dealt with one heap of poop, now over to the next. Guano. It is the excrement from seabirds, seals, and bats. Of course, we won't find the bats and the seals and the seabirds in the same place. Bats live in caves, and some people actually collect their excrement, and it is used as fertilizers. So guano is very high in nitrogen, and it's got even higher phosphorus levels. Grade 12s, I want to challenge you and think back about the previous slide with the 5 images. So we've done the manure and the guano. Which one was next in the top right corner? Give you a moment to think about that. Right, lime. The role of lime in the soil is to increase the pH, and that helps with the solubility of the NP and K compounds. The next picture was the very green one, which shows us crop rotation. And crop rotation indicates that a farmer won't plant the same crop in the same piece of land 2 years in a row. If he plants maize this year in a specific land, he might plant beans there the next year, because beans absorb different types of nutrients than corn would do. In that case, you avoid the total depletion of one type of nutrient in the soil. So specific plants absorb specific nutrients, and with crop rotation, you can avoid that. The last one is potash. It's an old-fashioned name for potassium, and that contains the salts of potassium, like potassium carbonate, potassium chloride, and potassium sulfate. This brings us to the end of all the theoretical stuff. We're going to look at paper 2 of the November 2019 grade 12 exams, and question 10 in particular. Grade 12s, it is very important that you must read the questions carefully and have a good look at what the problem statement is. In this case, the problem statement is very small, and it's actually consisting of 3 diagrams. So let's look at what they are asking us to do. Question 10.1 reads, the equation below represent 2 industrial processes involved in the preparation of ammonium nitrate. So in the bottom diagram, we have ammonium nitrate, which is the end product of process X and process Y. In question 10.1.1, they require of us the name of substance A. Substance A occurs in the first reaction of process X, whereby A plus 5 oxygens results in the formation of nitrogen monoxide and 6 water molecules. If we look at the reactions in process X, it becomes clear to me that they are representing the Ostwald process. And if we add something to oxygen and it must form a nitrogen compound, then it is naturally that A must be something that contains nitrogen. Let's look at question 10.1 again. They specify very, very clearly that it must be the name of substance A. So substance A must have something with nitrogen in it, and if you know your reactions, you would know that it is ammonia. Question 10.1.2, the formula of substance B. Substance B is the product of the reaction between nitrogen monoxide and oxygen. Nitrogen monoxide plus another oxygen gives us NO2. Question 10.1.3, the name given for reaction 1. If you remember correctly on the diagram, which they do not indicate there, and that is that there's actually a catalyst, a platinum catalyst. So the name of that reaction, the name of that little process, 10.1.3, is the catalytic oxidation, because we are adding an oxygen molecule of ammonia. Question 10.1.4. The name or formula of the catalyst used in reaction 1. I have by accident already answered that, and the name of the catalyst in this reaction is PT, the symbol for platinum, or you can write out platinum. Question 10.1.5. The name of process X. Remember when we did the slide with the reactions? I said for me, all the O's, the oxygens in the reactions with nitrogen, I relate to the Ostwald process. So that is indeed the Ostwald process. 10.1.6, the name of the process in Y. The end product of process Y is ammonia, and we had it in all three the slides where we looked at the reactions to form ammonium compounds, and that is our old famous Haber process. Question 10.1.7. Here they require us to write a balanced equation for the preparation of ammonium nitrate from the products obtained in process X and process Y. So in other words, the end product for process Y is ammonia to form the ammonium part of ammonium nitrate, and the end product for process X is nitric acid. So we have NH3 plus HNO3, and that forms ammonium nitrate. Is the reaction balanced? 1, 2 nitrogens on the right of the reaction and 1, 2 nitrogens on the left. Let's see, 3 oxygens, only 3 oxygens, and 4 hydrogens on the right hand side. So there we have 1 and another 3, that is 4. So the reaction is balanced just as it is. We do not have to add anything anything else to that. Question 10.2. A 15 kilogram bag of fertilizer contains 5% phosphorus, 10% nitrogen, and 15% potassium. Calculate in 10.2.1, the mass of phosphorus in the bag. It clearly states that 5% of the bag of fertilizer consists of phosphorus. So that means it is quite simple. It's 5%, it's 5 over 100 of what mass? Of 15 kilograms. And that is equal to 0.75 kilograms. So the mass of phosphorus is 0.75 kilograms. I want to highlight grade 12 that in this case we must be very careful. The problem statement actually provides us with percentages of NP and K and not a mass ratio. So therefore, it clearly states that 5% is phosphorus, 5% of 15 kilograms. We can and make it complicated by calculating how many parts consist of NP and K, and then you will see there are 30 parts altogether, and that 4.5 kilograms of the 15 kilograms consists of NP and K, and then we can again calculate 5 over 30 times 4.5 kilograms, and you get to the same answer of 0.75 kilograms. So just be very careful to read what they are actually asking and do not assume that they are referring to mass ratios automatically. So 10.2.2, they ask us what is the mass of the filler in the bag. If we can draw a little picture, so we already know that it's a 15 kilogram bag. We have 5% P, phosphorus, 10% N, nitrogen, and 15% potassium. So altogether that makes up 30%. So 30% of 15 kilograms is NPK, and therefore the rest consists of fillers. And so it is 100% minus 30%, which is NPK. So that leaves us with 70% of fillers. So the mass of fillers is equal to 70 over 100 times 15 over 1. And that should give us 10.5 kilograms. Grade 12s. This brings us to the end of the part on chemical industry, and I hope you've gained some insight and tips on how to tackle this section.